back to oscilloscopes here. So remember, we can measure the period or time of a waveform, and it does that in fractions of a second, such as milliseconds, meaning 1/1000th of a second, or microseconds, meaning 1/1000th of a second. And so these things can occur pretty rapidly. Even 60 hertz is 60 times per second, so that's pretty doggone fast. If you see something that happens, if a basketball bounced 60 times per second, it would be moving so quickly you would hardly be able to tell what's going on. So when you start talking about things that operate in much higher frequency, that would be even greater. So you can imagine, you get the idea. So frequency is the inverse or reciprocal of the period. And if we take a look here, we just take that, measure that time, and remember, we're measuring the full waveform, not just the time of one block. So obviously, this full waveform is taking 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those blocks. So whatever that time per division, we would have to multiply by 10. Then that would be our t. And then we've got to get the inverse of that. So this is 1 millisecond of time, which means our times per division has to be on 0.1 millisecond. So we start here at 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 1 millisecond. And then we get the inverse of that. That's 1 kilohertz, or 1,000 times per second. So you see that the smaller this number, the higher the frequency, and the lower this number, the lower the I almost said that right. Let's try it one more time. The smaller the number is, the higher the frequency. And if it's a pretty big time period, then our frequency will be lower. So they're inversely proportional is what I'm trying to say there. And we're going to do some more here. And notice now, we've got 2 full waveforms on this screen. And we're still at 0.1 volts, time per division, 0.1 milliseconds is what we're at. So here's 1 full waveform. Remember, we start at the reference line, go up, come down, come back to the reference line. We're going with the second one, going up, coming down, back to the reference. So now we're only wanting to measure 1 full waveform. So this is 0, 0.1, 0.2, 0.3, 0.4, 0.5. So this is 2 kilohertz. Notice this got smaller, frequency got larger. Again, inversely proportional. So how many cycles do we see here? And I'm going to work with you through this. It's pretty easy. We're starting at the reference. Up, down, back to reference. That's 1. Up, down, back to reference. That's 2. Up, down, back to reference. That's 3. So easy enough. All right, the time axis can also be used to determine phase relationship or phase shift of waveforms. Now, what we mean by that, and I would probably have to go back several slides, is if these things were in phase, the peaks would match the peaks, and the negative peak would match the negative peak. But obviously, these are shifted. The purple is to the left of the green. They're not on top of each other. And they're actually out of phase by 90 degrees. And we're going to see how that works here. So this thing teaches you one way. I'm going to teach you another. I like this second method. I'm going to pause the video and get a pen set up because we end up with the same answer. This is just much easier to me. So actually, no, this is the way it teaches. Painter teaches a different way, and I like this version better. So we'll go with this. So let's talk about first what we're seeing. If you get back to your math, remember sine, what it means, and this is a sine wave. When we look at a full waveform, that is 360 degrees. So we're looking at this purple wave. We're starting at the reference line, and we're moving back to the reference line, going negative and coming back. This represents 360 degrees of movement here. And if we take a look, it's talking about 50 divisions. Now, you're thinking here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Where are they getting 50? They're talking about these minor. There's 5 minor divisions in each of this. So basically this major division represents 36 degrees. These minor divisions represent 1/5 of that. So if I divide 36 by 5, we get 7.2, which is what they're talking about, these minor divisions. So each one of these little tiny tick marks represents 7.2 degrees of angle. So what they're saying is, and we can do this a little quicker just by knowing this is 36 here. So 36 plus 36 is 72. And then we've got 1 and about 2 more and maybe part of a third right here that gives us 7.2 each. So again, it's very subjective because I can see 1, 2, and it's somewhere between 2 and 3 here. But it's saying count those points. Let's zoom in and see if this tells us a little bit more. So it's saying there's about 12.5 right here, 5, 10, and then this is about 2.5 right here on this one. So that is 2.5 of the 36, or 36 plus 36, and then 7.2 plus 7.2, then half of 7.2. I'm probably confusing you more than I'm helping you by doing that, but it's easier to me to know each of these major divisions are 36 degrees, and all 10 of them make 360. So 36 plus 36 is 72. This is half of 36, which is 18. 72 plus 18 equals 90, just as using these minor divisions and having to say 12.5 of those times 7.2 gives us 90. It's a rose by another name. It's the same answer. I can just see those big marks better than I can those little marks, I suppose, is why I like that. And I can remember, I can divide by 10 easier than I can do this other way, but that's fine. It works. The math works either way you're doing it, because basically if we're using these little tick marks, we're dividing that 36 by 5, and we just have to take and count the number of small marks and multiply that times 7.2 for each one of those marks. So kind of whichever way you'd rather do it, but this is 90 degrees shifted is what it is. And we get that here. All right, so which quantity cannot be measured directly or derived by using a scope? We can measure voltage, because if I go back, voltage is the peak to peak, is from the top peak to the bottom peak. So yes, we can measure voltage. We can measure frequency, because we can take the period, invert it, and we've got the frequency, so that gives us that. And we can measure phase. That's what we just did back here, a little more complicated. But we can't measure resistance, so that's the right answer, so I skipped it on purpose. What value of an AC voltage does an oscilloscope directly measure? We get peak to peak. We see the little sine wave form, and it is peak to peak. So I'll have to answer resistance here just to get by. So peak to peak is what we get. Oscilloscopes classify the number of channels and bandwidth. I say most of our stuff's 50 to 100 megahertz. This one's actually, if I'm reading a little writing up there, 20 megahertz. It's typically on the scope, and it's typically fine for whatever we're using it for. We should have what we need. This is a single trace. Some are single trace, especially if you get into some of the older ones. I actually remember some that had round displays instead of square. That's going back many years there. Most that we see today are dual trace, but they make triple trace and quad trace. If we need triple trace or quad trace, we're going to have to set up another scope, but ours are typically dual trace here. And so we have 2 voltage inputs. We can display either channel 1, channel 2. We can do both, or we can do an add feature. We'll talk about that a little bit later. But we can see both waveforms simultaneously. Bandwidth is the highest frequency. This particular one's at 20 megahertz. So if we tried to measure something that had greater than 20 megahertz, our scope would not be able to handle it and just could not stop the waveform. Now that probably means we've probably got a little bit of wiggle room there. We might can measure something with 22 megahertz, but at some point we're going to get past the capability of the particular scope that we have there. And if we're looking at this kind of waveform, that's going to be a dual trace. We got a sine wave, we got a square wave. At minimum, this is a dual. It can't be a single. Could be a triple, and we're only using 2 channels, but at minimum, this is a dual. All right, so we've kind of hit the analog scope, and we'll look at the summary. We get to see the waveforms. We can't see that with a meter. We can get an RMS value of this peak-to-peak depiction that we have here. But and we could do the math and get the peak to peak, but we couldn't see that it's a nice, pretty sine wave like we see here. And we can measure that peak to peak. That's called amplitude. That's top to bottom, left to right, period. How often is it happening? This is one waveform every blank milliseconds, or one waveform every blank microseconds, just depending. And we can see the wave shape, sine wave. Some places call this a triangle, some call it a sawtooth. This is a square wave, and I've never heard what that's called. It looks like an EKG readout, but it's not any of those 3. So again, they come in single trace, dual trace, all the way up to a quad trace. We've got duals, and that's pretty much it. And as always, if you have questions, please let us know.